In this video, we are going to use Stokes' theorem to find the circulation of a vector field F around the curve C, where C lies on the intersection of the cylinder x square plus y square equal to 4 and the hemisphere x square plus y square plus c square equal to 16 and z bigger than equal to 0. The curve C is oriented anti-clockwise when viewed from above. So in general, the formula to find circulation of a vector field around a curve C is given by this. We take integral of the function m dx plus n dy plus p dz along this closed curve C in the space, where m, n and p are the components of the given vector field. Now Stokes' theorem says that we can find this circulation using the surface integral. So this integral on the left is equal to the surface integral of curl of the vector field F dot product n cap multiplied with d sigma. Now what is this n cap? This is a unit vector outward drawn normal on the surface S whose boundary is this curve C, and d sigma is a surface element. Now first let's find out the circulation along the curve C using this formula. For that we need to find the parametric form of the curve C. So let's look at the given surfaces. Cylinder of the radius 2, which is this surface here, and then we have the hemisphere of radius 4 on the positive side of the z-axis, which is this surface, and the intersection is this curve on the top here. This is the curve C. Okay, so how do we find its equation? We substitute x square plus y square equal to 4 into this equation. What do we get? We'll be eliminating x square plus y square and we'll have an equation in z square, which we can solve for z, and we get that the curve lies in the plane C equal to 2 square root of 3. Now it also lies on this cylinder, so we can find parametric equation of this curve. So the parametric equation of the curve C is 2 cos ti plus 2 sin tj plus 2 square root of 3k, where t varies between 0 and 2 pi. So now that we have the parametric form of this curve C, we can find this integral. For that, first we find the variables x, y, z and the functions m and p in terms of in the parametric form. Okay, so we can get from this equation, we find that the x is equal to 2 cos t, y equal to 2 sin t and z equal to 2 square root of 3. We find derivatives of x, y, z with respect to t and we get dx, dy, dz. Now we substitute these values in m and p. What are m and p? These are the components of the given vector field F. So after that, what we get is we get m dx plus n dy and p dz as a function of t. So now we can find this integral by integrating this function with respect to t. So it transforms into this nice integral in a single variable t with the limits from 0 to 2 pi, and this integral comes out to be equal to minus 8 pi. So this is the circulation of the given vector field along the curve C using this formula. Now let's find out this surface integral. For this we need to find out three things: curl of the vector field F, this unit vector n, and the surface element d sigma. So let's start with the surface S. The surface S is given by x square plus y square plus c square equal to 16, bounded by the curve C. Now if we look at projection of this surface on the xy plane, then the projection will be this circle x square plus y square equal to 4 in the xy plane. So how do we find the surface element d sigma? D sigma is equal to mode of the gradient of f divided by mode of gradient of f dot product p cap multiplied with dy dx, where f is our surface x square y plus y square plus c square equal to 16 bounded by the curve C, and p cap is this unit vector which is perpendicular to the shadow of this surface on the xy plane. Now the shadow of this surface is this circle of radius 2 in the xy plane, and the unit vector which is perpendicular to this shadow is k cap, the unit vector along z direction. So we have p cap, and what is gradient of f? F is this surface bounded by the curve C, so gradient of f will be equal to take derivative of this surface with respect to x, y and z. So we get gradient of f equal to 2xi plus 2yj plus 2zk. Now what's the magnitude of gradient of f? It's equal to this function. Now the important thing to notice is that this point x, y, z lies on the sphere, and for every point on the sphere, sum of squares of x, y and z is equal to 16. Therefore, this value will be equal to 8. So now we know the unit vector p cap, mode of gradient of f we can find, and gradient of f we can find dot product of gradient of f and p, and it turns out to be equal to 2z because z is non-negative. So we can find the surface element d sigma by substituting these values in the formula. Now let's look at n cap. N cap is this unit vector given by plus or minus gradient of f divided by mode of gradient of f, and we know the value of gradient of f. So how do we decide which sign we have to choose, positive or negative? For that, we pick some point on our surface, we substitute coordinate of this point here, and if we get an outward drawn normal to the surface, then we have to choose positive sign. Okay, I mean, in case we choose a positive sign and we get an outward drawn normal, then that means we chose the correct sign. Alright, so now we have the surface element and n cap. Now we need to find curl of the gradient, curl of the function given vector field f. So curl of the vector field f is given by determinant of this matrix, where the third row is the component function of the given vector field f. So we find the determinant, and it turns out to be equal to 3x square y square k cap. So we already calculated the unit normal vector, so we can find dot product of curl of f and n cap, which is equal to this nice function, and we substitute all these values in the surface integral here in this formula, and this surface integral transforms into this nice surface integral where we can cancel out the z variable, and we have this surface integral in two variables x and y, which we need to integrate with respect to dy dx. So we can find this integral using rectangular coordinate, or we can use polar coordinate. It will be easier if you use polar coordinate, and in this case we find it using the polar coordinate, and the answer turns out to be, let me move the page, the answer turns out to be equal to minus 8 pi, which is same as the value we calculated using the first formula. this line integral. So this shows us that the circulation of vector field around the curve C is same using both the formulas. That means Stokes theorem is correct, and it also gives us two ways to find circulation of a vector field around the curve C. So if you are asked to find just the circulation of a vector field around a curve, we can use the first formula. But if you are asked to prove Stokes theorem for the circulation, then we need to find both of these integrals and need to show that they are equal. And if you are asked to use Stokes theorem to find circulation around the curve C, then we have to find it using this surface integral.